Good morning, friends. In previous class we studied limits, we studied tolerances, and we also studied why we study the limits, why we study the tolerance, and we saw that these all limits come into picture because a product cannot be manufactured of the exact size. What I want to mean by exact size is that when we go on manufacturing a shaft, say a shaft we have to manufacture of 50 mm diameter, then suppose we are manufacturing 50 shafts, or you can say we are manufacturing 100 shafts, each of 50 mm diameter we have to manufacture, but this is not possible. When you manufacture and measure, you will find that someone is more than 50 mm, someone is less than 50 mm, and by chance some shafts may be of 50 mm, but it will be rarely that a shaft will be of equal to 50 mm. What we want to say is that when we go on manufacturing a 50 mm shaft, the shaft will be manufactured of 50 plus A 2, or you can say like this, ignore this, you can manufacture from 50 minus A to 50 plus B mm shaft. That means there is a deviation. The minimum limit of the shaft is 50 plus minus A mm, and the maximum limit of the shaft is 50 plus B mm. So what we are actually getting is that there is a deviation between the maximum limit size of the shaft and minimum limit size of the shaft, and that is nothing but A plus B. There is variation of A plus B unit, or you can say mm, and this variation or deviation in the shaft manufactured will be known as tolerance. Now let's understand this concept of limits in more detail. Suppose we have to manufacture this, suppose that this pen is of diameter 8 mm. So we have to manufacture 8 mm diameter stylus pen, but when we go on manufacturing, suppose we manufactured 5 pieces, then each of the pieces will be of different dimensions. They will be of 8 mm, but there will be slight variation. And what I want to say is that suppose this is 8 mm pen, so when we go on manufacturing, maybe that the one is 8.01 mm, the another is 8.02 mm, the third one is 8.05 mm, the fourth one is 8.04 mm, and let the sixth one is again fifth one is 8.03 mm. So we see that each dimension are different, and the maximum dimension is 8.05 mm. The pen which will have the maximum dimension will be of 8.05 mm, and the pen which will have the minimum dimension will be of 8.01 mm. This is minimum and this is maximum and minimum. So this is the maximum 8.05 will be called as maximum limit size, and 8.0401 will be called as minimum limit size. So we studied all those things in the previous class. In the previous class we also studied the definition of hole, and we through demonstration watched that a hole need not necessarily be round. a shaft also need not necessarily be round. The cross section of the either the hole or the shaft can be any shape, that can be trapezoidal, that can be a square, that can be rectangular, or that can be oval also. So we tried to understand the definition of hole and shaft. We also studied in the previous class that a same feature, a same physical part which behaves as a hole for one assembly may behave as a shaft for the other assembly, and for this we took the example of the mobile phone which behaves as a hole for the charger connector, and which behaves, the same mobile phone will behave as a shaft for the cover of the mobile phone. Next we studied accuracy and precision. And through example of pages, counting of pages of a notebook, we saw that to a student understand the one student counted one side of the page and the other side of the page as two page, and one student counted both sides including as a single page. Another student counted 4 pages, that is was complete sheet of a notebook as a single page. So we also saw in that class that the precision, though it is quality is good, quality of measurement is good, but the accuracy may not be achieved, or you can say quality is good but it is not correct to the not exact same as the true value. So precision does not ensure the correctness of the measurement, but it may ensure the quality of the measurement. We studied that accuracy is the comparison of individual measurement with the true value, and precision is the closeness of the different measurement, or you can say in simple sentence it is repeatability of the measurement. So in today's class we will now move forward and we'll now see in today's class some standards which are adopted for the fundamental deviation and standard tolerances. So today's class are fundamental deviation, and standard tolerances. So first of all, let's understand the term what is fundamental deviation. This is a zero line. We want to manufacture a shaft, and the shaft we manufacture is something like this. Okay, this is the lower limit size of the shaft, and this is maximum limit size of the shaft. So lower limit size, and this is the maximum limit size of the shaft. So the fundamental deviation is the lowest deviation, or you can say the deviation which is nearest to zero line. This is the zero line, so this deviation is nearest to the zero line, not this deviation. This is the upper deviation. This distance is more and this distance is less, so this distance will be known as fundamental deviation. Now take another example of a shaft. Let this is the zero line and shaft is below the zero line. So in this case, this is the deviation which is nearest to zero line, so this deviation will be called as fundamental deviation. This deviation is not nearest to zero line, its distance from the zero line is more, this distance is more as compared to this distance, therefore only this distance will be called as fundamental deviation. So fundamental deviation, we are understanding this through arbitrary example, but ISO 286/1988 and for India, Bureau of Indian Standards Code is IS 919 1993. They have some standardized fundamental deviation, and so in today's class we will study standardized fundamental deviation. After completing this fundamental deviation topic, we will move on to standard tolerances. So let's understand the various standardization for fundamental deviation. So this is the zero line, this is the zero line. Now this is one standardized fundamental deviation. It will be called as A. It will be called as A. This is another standardized fundamental deviation. It will be called as B. There is another standardized fundamental deviation. It will be called as C, and so on. It will move, and there is another standardized fundamental deviation that will be called as H. After that, there will be J and J's. Another thing, it will move to ZA, ZB and ZC. So since we are writing the alphabets or combination of either the alphabets or combination of alphabets in capital letter, this capital letter in the standard, in the code, is used to represent the fundamental deviation for the whole. If you want to show the fundamental deviation for the shaft, the alphabets will be in a smaller case. So fundamental deviation of shaft is represented like this. This is the fundamental deviation of shaft. This will be called as A. Fundamental deviation of another fundamental deviation for shaft B. All these will be represented by a small letter, and it will move to a small h. This is the fundamental deviation for shaft a small h. Next there will be J. There will be J and J's, and then it will move to Z a small a small z, a small v, a small z, a small c. So all these are a standardized fundamental deviation. When we say a fundamental deviation A, this fundamental deviation for whole A, that means that its distance, the lower is the deviation which is closest to zero line. This deviation is closest to zero line. This deviation is closest to zero line, and this deviation will be fixed. For A it will be fixed. For the basic size should also be the same. Suppose that we have to manufacture a hole of 50 mm diameter. Then for 50 mm diameter, for this A type of fundamental deviation, this value will be fixed by a formula provided by ISO 286-1988, or you can say IS 919-1993. These two codes are similar. The Bureau of Indian Standards have accepted totally without any change the code of ISO 286-1988. So when we come to fundamental deviation B, this fundamental deviation, this will also have a formula, and for this fundamental deviation, this distance will be known as the fundamental deviation value, and this fundamental deviation value will have a formula, and that formula will be, suppose that for 50 mm diameter, if we take the B fundamental deviation, the fundamental deviation value will always be same. Since we are saying that it's B fundamental deviation, that means we are defining the fundamental deviation, and since the fundamental deviation is defined, its value will be fixed. If not fixed, how it will be defined? So if you are understanding this part, similarly we can move on. And when we move from like this, let this see ZA. So this is the whole. So fundamental deviation for ZA whole, this deviation is the fundamental deviation for ZA whole, and this will also have a formula. But there is one twist here. The twist is that when we saying the fundamental deviation of A, this is the lower deviation. This is the lower deviation. But when we are saying the fundamental deviation of ZA, so this deviation is the upper deviation. So when the hole is above the zero line, fundamental deviation will be the lower deviation or E-cart inferior, and when the hole is unilateral, that is on the one side of the zero line, but it is below the zero line, then in that case it will be the, or you can say the fundamental deviation will be the upper deviation or E-cart superior. Now come to the fundamental deviation of the shaft. For fundamental deviation of shaft also, for this A value will have a particular fundamental deviation value. This A fundamental deviation will have a certain fundamental deviation value, or you can say will have a certain distance from the zero line. Similarly, B will have another certain distance. Yes, if we take the 50, if we take basic size at 50 mm, then absolutely the fundamental deviation of A, this distance, will be more than the absolute value of fundamental deviation of B. It will also be valid for hole also. For hole, let this distance is y1 and let this distance is y2, then y1 will always be greater than y2 for the same basic size. If we change the basic size, the value of fundamental deviation for y1 and y2, let we change the basic size from 50 mm to 100 mm, then y1, then this y1 value will change and y2 value will change, but again for 50 mm, for 100 mm of basic size, y1 will always be greater than y2. So for shaft, for A fundamental deviation, the fundamental deviation of A is nothing but the E-cart superior, since it is below the zero line. And for shaft such as ZA, or you can say ZB, let this ZB, the fundamental deviation will be nothing but this minimum, or you can say lower deviation, and that is lower deviation means this is E-cart inferior. We let shortly discuss the sign. If we write ES, E-cart superior, in capital and E-cart inferior in capital, then they represent the deviation for holes. And if we represent a small es and a small ei, then they represent the deviation for shaft. ES means E-cart superior, means this is representing the upper deviation. E-cart inferior, since inferior it is representing the lower deviation. And in the similar way for shaft, this E-cart superior is representing the upper deviation and E-cart inferior is representing the lower deviation. Upper deviation and lower deviation concept we have already discussed in the previous class. So let's now understand the further explore the standards given by the ISO for fundamental deviation. What we are doing is that we are starting, let's first consider for hole. We are starting from A, we are then going to B, then C. After C, and suppose I am again drawing this diagram, there has been some mistake, and let this is A, this is B, and same we will move further, and here will be H. H is the fundamental deviation for hole whose lower limit is 0. Sorry, not lower limit, whose lower deviation is 0. Whose lower deviation is 0, that is it matches with the 0 line. When we move A to B, so B, then C, there will be C, after C there will be D, E, F and G. In between CD there will be another fundamental deviation, and that will be combined, that is known as CD. Together we will write. So C is one fundamental deviation, CD is another fundamental deviation, and E is another fundamental deviation. Again, between E and F there is another fundamental deviation, and that is known as EF. So E is one fundamental deviation, EF is another fundamental deviation, and F is again another fundamental deviation. In the similar way, between F and G, there is another fundamental deviation, FG. So F is one fundamental deviation, FG is second fundamental deviation, and G is the third fundamental deviation. So what we are seeing is that, 1 minute please. Let me delete all these things to make you clear. Okay, so in this way, H, after H there are fundamental deviation J and J's, and then we move to Z. After Z there is fundamental deviation ZA, then there is fundamental deviation ZB, then there is fundamental deviation ZC. So how many total fundamental deviation are? Let's count it. So let's count it. A to Z in the English alphabet there are 26 letters. So 26 is this one. After that there are CD, EF, FG and JS. So these are 4 fundamental deviation are added. After that there are 3 more fundamental deviations, ZA, ZB and ZC, and these are 3. So altogether these are 33. Out of these 33, there are some alphabets which are not considered as fundamental deviation. These are I, L, O, Q and W. These I, L, O, Q, W letters of the alphabet are not under the fundamental deviation as specified by ISO 286/1988. So we will eliminate this fundamental deviation from this 33 count. These are 5 in number. So 33 minus 5, there are altogether 28 fundamental deviations. So there are altogether 28 types of fundamental deviation for whole. Similarly, there are also 28 types of fundamental deviation for shaft. So let's understand the fundamental deviation for shaft. So this is A fundamental deviation for shaft, this is B, this is C, this is D, this is E, this is F, and this is G, and this is H. After this H, whose upper deviation is 0, after this H there are J and J's, and then it will move on. There will be Z, there will be ZA, there will be ZB, there will be ZC. So these much of fundamental deviations are possible, and they are same as the whole but represented in lower case. So there are 28 types of fundamental deviation for shaft also. Now the fundamental deviation capital H, the whole which is having fundamental deviation of capital H is known as basic whole, and the shaft which is having the fundamental deviation of a small h, since shaft fundamental deviation is represented by a small h. So this fundamental deviation is known as, the whole representing with this fundamental deviation will be known as, shaft with this fundamental deviation will be known as basic shaft. Now let's understand one interesting facts about the fundamental deviation for hole and shaft. From A till H, from A fundamental deviation of shaft to H fundamental deviation of shaft, the value of fundamental deviation for shaft A will be same as the value of fundamental deviation for hole A. Similarly, the value of fundamental deviation for shaft B will be same as the magnitude of the value of fundamental deviation for hole B. Magnitude wise, the fundamental deviation value for same type of hole and shaft are same magnitude wise, but they are on opposite side of zero line. That means that if the fundamental deviation of shaft A is some minus x, then fundamental deviation for hole A will be plus x, because the fundamental deviation for hole A is above zero line, that will be positive, and fundamental deviation of shaft is below zero line, that will be negative. In other words, we can understand like this: the fundamental deviation for shaft is nothing but E cart superior. So E cart superior for shaft will be equal to, let hole is here, fundamental deviation is this one, and this is nothing but E cart inferior. So E cart superior of shaft will be equal to negative value of E cart inferior of hole for the same type of fundamental deviation. That is, for fundamental deviation A, this E cart superior will be minus E cart inferior of the hole. This type of relation for the corresponding fundamental deviation exists up to fundamental deviation of small h, or you can say the fundamental deviation capital H. For hole it's capital H, for shaft it's a small h. After a small h / capital H, there is no generalized relationship between the fundamental deviations for hole and for shaft. I am not telling that the fundamental deviation of the two can't be same, but it cannot be generalized. It can be same for some purposes, but it cannot be generalized. So now we are going to understand unilateral and bilateral tolerances. So next topic is, this is also related with the fundamental deviation. So now we'll understand unilateral and bilateral tolerances. Unilateral and bilateral tolerances. Again, draw the fundamental deviation, a standard fundamental deviation. This is fundamental deviation capital A. This is the fundamental deviation, means lower limit is fixed. The fundamental deviation only representing the fundamental deviation. The upper limit cannot be fixed. The upper limit cannot be fixed. So what will be the upper limit? Upper limit will depend on what deviation in the limits is allowed, or you can say what tolerances we are providing. This is the tolerance. This deviation in size is nothing but the tolerance. If tolerance is this much, the upper deviation will be this much. If tolerance, fundamental deviation is fixed, I have told, the A लिख देने के बाद fundamental deviation fix हो गया. So upper deviation, suppose that the tolerance is this much, then this will be upper deviation. In this case, this will be the tolerance. So by applying the fundamental deviation, we are only fixing one of the limit. That may be maximum or the minimum. Here it's minimum limit, or you can say the lower deviation. So whenever we are increasing the tolerance or decreasing the tolerance, you can increase the tolerance, you can decrease the tolerance. If fundamental deviation is specified, this is the fundamental deviation, letter A means the fundamental deviation is specified, and this is the fundamental deviation value, then in that case the whole of the zone or the variation, or you can say the tolerance zone, will be shown only on one side of the zero line. You can understand like this. A will always be above the zero line. B will always be, B is also something like this. B is always above the zero line. Or you can say A, B, C, D up to H are above the zero line. Or you can say on one side of the zero line, when the tolerance zone can be represented on one side of the zero line, then they are known as unilateral tolerance. So from A to H, for fundamental deviation from A to H, all the tolerances will be unilateral tolerance. Similarly, come to the ZA, ZB, ZC, or you can come to P, R, S, T, V. All these fundamental deviation for whole will be represented below the zero line, that is on one side of the zero line. Then these fundamental deviations are also unilateral tolerance. Fundamental, the whole with fundamental deviation Q, R, S, P, Z, ZA, ZB, ZC will be below the zero line and will be called a unilateral tolerance. So there are some fundamental deviation like ZS. ZS is represented something like this. Means ZS, one limit is above the zero line and another limit is below the zero line. That means the tolerance zone will cross the zero line, and such type of fundamental deviation which represent the tolerance, and then tolerance will be called as the bilateral tolerance because they are on both sides of the zero line. So ZS fundamental deviation, either it is for whole or it is for shaft a small js, both will be bilateral tolerances. There can be other bilateral tolerances like tolerance with fundamental deviation M. It can be, or it sometimes it cannot be bilateral tolerance. So we have understood the concept of unilateral tolerances and bilateral tolerances. Now we do a quick assessment of what you have understood from the ongoing classes of 32 minutes. So let's come on, understand what you have understood. So we are conducting an assessment, a short assessment. Let's everyone who are online participate enthusiastically. So first assessment, first question. Fundamental deviation, let's listen and answer. Fundamental deviation defines the position of tolerance zone with respect to zero line. Fundamental deviation defines the position of tolerance with respect to zero line. You have to state true or false. So it's true. It's true. How? When we specify the fundamental deviation, we are specifying one limit. One limit is specified, and after that, depending on the tolerance, the other limit will vary, but one limit is not going to change. Means one position is specified. So it specifies the position of the tolerance zone with respect to zero line. Second assessment. Tolerance specification is written as 40D8. What does letter D represent? Does it represent a whole or a shaft, or it represent a fundamental deviation? So we have already seen that A, B, C, D up to Z, C, which are 28 in numbers, represent fundamental deviation. We have been studying fundamental deviation. So letter D represents fundamental deviation. come to third question. CD, this is one of the fundamental deviation. Since these are written in capital, this fundamental deviation is for whole, fundamental deviation for whole. So CD and this a small CD, this is also the fundamental deviation, but this is for shaft. So we have to tell that what is the distance of fundamental deviation of CD and fundamental deviation of CD, that is for shaft, will be the same. Yes or no? Answer is yes. From A to H, the distance are same for same type of fundamental deviation from the zero line, but they are on the opposite side of the zero line. So they will be same, but they will be opposite side of the zero line, or magnitude wise they will be same. But if we want to consider the sign, then the fundamental deviation of capital CD will be minus of fundamental deviation. Fundamental deviation of capital CD will be minus of fundamental deviation of a small CD. Okay, since this will be above the zero line, this will be below the zero line. So we are talking that each fundamental deviation have a particular value. Each fundamental deviation, when we say a fundamental deviation, then it will have a particular value, and there are some standard formula for this, like for shaft A, for shaft with fundamental deviation A, there is the formula minus 265 plus 1.3D plus 1.3D plus 1.3D for basic size less than or equal to 120 mm, and it is equal to minus 3.5D for basic size greater than 120 mm. Means the fundamental deviation are depending on the basic size. It in fact depends on basic size. So but it's not so that the formulas are also different. Since this is in formula we are using this D, so it depends on the basic size. D is not the basic size, but D is derived with the help of basic size, or it denotes basic size. It's not exactly the basic size. So what we are getting is that this is the basic size, so the fundamental deviation value depends on the basic size, but we are having two formula for two different group of basic size, but it's not necessary. For B also it is like that, we have two formula. For fundamental deviation C also we have two formula. For fundamental deviation CD we have only one formula, and for fundamental deviation D we have the formula minus 16 D पे power 0.44. D, a small d, means fundamental deviation for shaft. A small d fundamental deviation for shaft is below the zero line, and so it is, the sign is negative, minus sign. 16 D is geometric mean diameter, which is related with basic size, power 0.44. For E also for D we are having only one formula, but that also depends on the basic size. For E we have another form, we have the formula minus 11 D power 0.41. For F we have another formula, for EF we have another formula, and in this way. So what will be the fundamental deviation for H shaft? This is the zero line, and this is H shaft. This is the fundamental deviation, but deviation which is nearest to zero line, this deviation is nearest to zero line, and this matches with the zero line. So fundamental deviation for this H shaft is 0. So now we will study the standard tolerances, and again we are studying the ISO 286 1998 and IS 919 1993. So now we will study standard tolerances. Standard tolerances. According to the code which I told you of ISO and BIS, there are 20 grades of like fundamental deviation. How many fundamental deviation? 28 types of fundamental deviation for a hole as well as for shaft. Similarly, there are 20 grades of standard tolerances. Standard tolerances for basic size up to 500 mm. If basic size is 500 mm, there are 20 types of tolerances, and if basic size is greater than 500 mm, or you can say write like this: basic size is greater than 500 mm, but it is less than equal to 3150 mm, then there are only 18 grades of standard tolerances. Standard tolerances. So in engineering practices, we are mainly encountered with shaft or holes whose basic size is generally less than 500 mm. So we will only study those 20 types of standard tolerances. So the tolerances are something like this: IT 1, IT 2, IT 3, IT 4, IT 4, IT 5, and then it comes IT 6, and so on. We will move to IT 18. These are 18 in numbers. After IT 1, there was discovered one more tolerance whose width or the value of tolerance was less than the value of IT 1, and it was named as IT 0. It was named as IT 0. It is same like that first law of thermodynamics. Another law of thermodynamics was observed, and that was named as 0th law of thermodynamics. In the similar way, IT 0 was analyzed after IT 1, and again after 0 was in use after some years, there one tolerance need of one another tolerance was held whose value was less than the value of IT 0 for same basic size, and that was named as IT 01. So this IT 01, IT 02 in number, then IT 1 to IT 18, they are all together 20 grades of tolerance, a standard tolerance for basic size up to 500 mm. So what does this IT 01, IT 0, IT 1, IT 2 and so on up to IT 18 implies? How they represent the value of tolerance? Now we will discuss on this point. So suppose we are writing IT 16, then the value of IT 6, then its value is 10i. When we write IT 7, its value is 16i. When we write IT 8, its value is 25i. What we are observing is that the value of the each succeeding IT is 1.6 times of the preceding IT. So value of IT7, that is 16i, is 1.6 times of 10i. And in the similar fashion, value of IT8, that is 25i, is 1.6 times, approximately 1.6 times of value of IT7, that is 16i. 16i into 1.6, that is 25.6, and that in a round figure it is written as 25i. This type of situation is observed from IT5. Value of IT5 is 7i. From IT5 till IT18, each succeeding IT value is 1.6 times of its preceding value. And when we go in mathematics, 1.6 is approximately equal to 1.58, and that is equal to 10 power 1 by 5. Means each succeeding value is being multiplied by 10 power 1 by 5 approximately. Means it's a geometric series, but it has a particular ratio, and this type of geometric series which is multiplied by 10 power something, the power is 1 by 5. Here it's 5, so it's called as R5 series. It will be called as R5 series. So grades of tolerances from IT5 to IT18 are arranged in R5 series. These R5 series is a special type of preferred series. Such type of series are known as preferred series. The numbers in this series are known as preferred number, and when we make the product in this series or in these sizes, they are known as preferred sizes. So this is R5 series, or you can say R5 series is one type of preferred series, or you can say preferred number, or you can say preferred size. Preferred size. Preferred size. There are other preferred series or preferred sizes like R10 preferred series, like R20 preferred series, R40 preferred series, R80 preferred series. So altogether R5, 10, 20, 40 and 80, there are five types of preferred series. These 5 types of preferred series are known as basic preferred series. So these are basic preferred series, or you can say 5 basic preferred series. Based on these 5 basic preferred series, that is based on R5, R10, R20, R40 and R80, we get some derived preferred series also, So we are not going in detail on what these preferred series are. You can refer any standard book on design of machine elements, or any book on metrology. It may not be available in all the book of metrology, but they will surely be available on design of machine elements. So now we'll move back to standard tolerances. the standard tolerances. So IT1 to IT5, they are also in a exact geometric series. The value of IT1 is 0.8 plus 0.02 D, and this value is known as A for the IT1. After A, when we move to IT2, its value is A into R. IT3 value is A into R square. So again we are seeing that we are to get the value of the next number in the series, we are multiplying the previous one with a particular value or a particular value we can say, that is R, particular factor, that is R. So from IT1 to IT5 are exact geometric series. They are each time multiplied by R. They are not multiplied by 1.6 roughly. In preferred series we are not multiplying exactly with 1.6. That they were called as preferred series. Now we are multiplying exactly with R, and so from we will say that tolerance grades, standard tolerance grades from IT1 till IT5 are arranged in exact geometric series. Come to IT0 and IT1. IT01, the value of IT0 is 0.5 plus 0.012 D, and the value of IT01 is 0.3 plus 0.008 D. What we are seeing is that we are not having any series for IT01 or IT0, and again for IT1 we are having a value. This is the initial value which is being multiplied with a particular value R to get the next tolerance grade value. But these three, IT01, IT0 and IT1, are having some formula, a specific formula, and these are known as empirical formulas. So IT01, IT0 and IT1 have empirical formulas. So now we will do a simple assessment. Students who are online, are the students who are seeing the recorded video are requested or are advised, in fact advised, to pause the video and solve or try to solve at least the example or the assessment I am going to put forward. So let's take the example. Example is a hole is designated as 25H7. So what is H? H is the fundamental deviation. What is 7? 7 is tolerance. 25H7 means that this is a hole. 25H7 is a hole whose basic size is 25 mm, whose fundamental deviation is H, and whose tolerance grade is IT7. IT7 means 69. So now come to what the question is. Question is something like this: 25H7 hole has the minimum limit size as 25 mm and maximum limit size as 25.021 mm. The another data given is the hole with 25H8 has the minimum size as 25 mm and maximum size as 25.033 mm. Now the question is, if the hole is 25H6, then the minimum size is 25 mm. It is given and it is asking what will be the maximum limit size. What will be the maximum limit size? maximum limit size. So what we are observing is that the tolerance for this shaft, that is for shaft for hole 25S7, the tolerance is 0.021. Tolerance for hole 25H8 is 0.033 mm. So what will be the tolerance for this? If you have observed that from IT6 or IT5 to IT18, all the tolerance grades are arranged in preferred series, that is each succeeding IT value is obtained by multiplying the preceding IT value by 1.6, approximately 1.6. So since this is IT6 and this is IT7 value we know, so if we divide by 1.6 we will get the IT6. Reverse we have done, IT6 multiplied by 1.6 is IT7, so IT7 divided by 1.6 will be value of IT6. So what will be the value of IT6? So IT7 0.21 divided by 1.6, and that comes to be 0.013 mm. This is the tolerance. And what is tolerance? Tolerance is maximum limit size minus minimum limit size. Maximum limit size is not known, let's it's x. Minimum limit size is 25, so x minus 25 is 0. How much this is? 0.03 mm, 0.013 mm. So x is nothing but 25.013 mm. This is the maximum limit size. Maximum limit size for hole 25H6. So it's very simple question. Now next to the move to the next assessment. Before that we have to give me one important part or important data from the ISO. ISO tells that we have the standard tolerance up to IT18, but if in future if there is need of other tolerance whose value is more than IT18, then that tolerance will be named as IT19. After that, if there is again a need, then that tolerance will be named as IT20, and the value and all these tolerances will be in the R5 preferred series. So if the value of IT18 is late, it is 20, not late, it's exactly 2500I, then the value of IT19 will be 2500I into R5 series, that is multiplied by approximately 1.6, and that will be 4000I. Similarly, the value of, to get the value of IT20, multiply this 4000I into 1.6, and we will get 6400I. So my assessment question is something like this. Question is like this: we are given the value of IT18 as 2500I. Now you have to extrapolate the value of IT21 and IT22. So to get IT21, what we will do? We will do IT20 into 1.6. To get IT20, we will do IT19 into 1.6. This will be IT20, and then we'll multiply with this 1.6. To get IT19, what will do? IT18 into 1.6 will be IT19, then multiplied by this 1.6, and then again this one 1.6. So what is the value of IT18? 2500i. Now 1.6 into 1.6 into 1.6, and this value is this is 4000i, 6400i, and this is 10,000i. So this value will be 10,000i. Now find the value of IT22. What is IT22? That is nothing. It's easy, much easy. IT21 into 1.6, that is 16,000. That is 16,000i. 16,000i. Now we have been using I frequently, but what this I is, we have to understand it. According to ISO 286, I is 0.45 d power 1 by 3 plus 0.001 d, where d is geometric mean diameter. Geometric mean diameter. Now what is geometric mean diameter? Geometric means the geometric mean of the two values. Then what is those two values? So ISO is also specified some steps. The shaft lying between these two range will have a particular geometric values. And what are those range? Take a simple example. From 0, excluding 0, a value greater, the shaft is having a value greater than 0, but less than, but up to 3 will be in one range. So all the shaft whose diameter is greater than 0 and up to 3 will be in this range, and its geometric mean diameter will be root under 1 into 3, and in place of 0 write 1, in place of 3 write 3. For shaft 3, value for shaft whose basic diameter is greater than 3, it should not be 3. If it's 3, it will be in this range. If it's greater than 3, come to the next range. Greater than 3 but up to 6. 6 को include कीजिए, 3 को exclude करना है. Then the geometric mean diameter GMD in that case will be root 3 into 6. So suppose that we have to design, and other range are 6 to 10. Then other range is 10 to 18. This is open bracket and this is closed bracket. You have studied in math in set theory what is the meaning of open bracket and closed bracket. We are not going on that. So next is 18 to 30. This 30 to 50, and so you can suppose a shaft is having a value basic diameter as 25 mm. So this will lie in this range, and so geometric mean diameter D will be root under 18 into 30. Now let's imagine another shaft which is having a value 30 mm, which is also lying in this range, and its geometric mean diameter will also be 18 into 30. Now imagine a shaft whose basic size is 20 and 20 is also in this range, and so its geometric mean diameter will again be 18 into 30. Now imagine another shaft whose basic diameter is 18. 18 is not in this range, it is in this range, and so for basic size 18 mm, geometric mean diameter will be 10 into 18. 10 into 18. Once on the, if basic size diameter is given and you have found a geometric mean diameter, you will find the I value, and I value is 0.45 d power 1 by 3 plus 0.001 d. Now you have to understand one thing. This d value will be put in this formula. This d value are put in mm, and the I value, after putting the d value, what we get the value of this hole, that is the I value, E will be in micrometer. Since this is an empirical formula, Dimensionally the left LHS will not be equal to RHS. So this will be in micrometer. So if we have found I as, suppose that we have found it as 19.9 micrometer. So 19.9 micrometer is approximately 20 micrometer, and that is 0.02 millimeter. So this is the what we are calculating I value. Then we will calculate suppose a shaft is having 16i, then we will calculate this or 10i, then we will do 0.02 into 10, and it will be 0.2 mm. So in this way we can calculate the tolerance value or the IT value, and it's easy. So, and then we will use this tolerance to find the limit of the shaft or the hole. Now we will move to another small assessment. Again, assessment is must to understand the topic. Assessment is must. So move to the assessment. The first assessment is find the size limits. Find the size limits for the whole 25F7. How will find it? So for F we know the formula. We can find the fundamental deviation. Whole F will be above the zero line. This is zero line, so this will be the fundamental deviation value from F. From the literature we can find the value, this value, and then it is written 7 means IT7 means 69. So first you find I, and since 25 है, 25 के हेल्प से आप D निकालेंगे, D का वैल्यू रख करके I निकालेंगे, माइक्रोमीटर में आएगा, उसको मिलीमीटर में कन्वर्ट करके यहाँ रखेंगे, और जब ये वैल्यू आ जाएगा then will know the what is tolerance. So this distance and this distance, if we add to the basic size, will be this much. So this will give the upper limit. So in this way we can find the upper limit and lower limit. Next assessment is the same but it's shaft 25F7. So shaft F is below. From the formula we can find what is this distance, then what is the value of this IT7 we can easily find, and then we can find what is this limit and what is this limit. This is the upper limit and this is the lower limit. Now what we have observed one thing, when we are telling 25F7 capital F7, 25 capital F7, when we say 25 capital F and 7, all these three together, then a whole is represented. If you say only capital F, a fundamental deviation is represented. Only 25, oh, it represents only the basic size, and 7 represents only IT7, that is the grade of international tolerance grade. I means international, T means tolerance, IT international tolerance grade. So to represent a hole or a shaft, we have to specify the basic size, the fundamental deviation, and the tolerance grade, a standard tolerance grade. Alright. Now we will move to designation of fit. Designation of fit. We'll move to designation of fit. We have seen how we designate the shaft, basic size, fundamental deviation, and grade of tolerance. Now we'll move to designation of fit. So what is feed? First we have to understand this part. Feed is nothing but assembly of hole and shaft. In manufacturing, when we manufacture the product, one part of manufacturing is assembly also. We assemble various products, and during assembly one part is inserted inside the another. We have in previous class we have already studied clearly and also involved in activities what is hole and what is shaft. When we assemble hole and shaft together, a feet is generated. But then why we called feet? Why not we simply call as assembly? The reason is that the feet also defines the quality of assembly. It defines the quality of assembly, means when we are going to assemble one part with another, does this part, let this is shaft and this is hole, does this move inside this easily, or there is gap between these two, or does this size is such small that it cannot insert inside this hole? That means we have to apply some force to insert. If we apply the force, it may be inserted. So feet is the relationship between hole and shaft, but is the relationship, and it also defines the quality of assembly, that is the whether we have to, it will move inside the hole easily, or we have to apply the force. So these are the feet. Means to represent the feet, to designate the feet, we have to designate the hole as well as the shaft. So if we write like this, 20G7/F8, then G is in capital, fundamental deviation of hole, F is fundamental deviation of shaft. So this is the feet whose basic size is 20, means that basic size of hole is 20, as well as for the shaft is also 20. Fundamental deviation for hole is capital G, and fundamental deviation for shaft is a small f. Tolerance grade for hole is IT7, and tolerance grade for shaft is 8, means IT8. So in this way we designate the feet. Means we are designating the hole and shaft. What actually it is, means 20G7 hole, it is assembled with 20F8 shaft. But we are not writing 22 times, they will be common. For the same basic size we define the feet. The basic size for hole and shaft has to be same for the feet. So we are only writing 20G7/F8. In place of slash we can write like this, 20G7-F8 or 20G7/F8, or by we have written already like this, 20G7/F8. So these are the way we can designate the feet. Now we have to understand, when we have come to the feet, now we understand hole basis system and shaft basis system. Hole basis system and shaft basis system. So first come to hole basis system. Hole basis system. Hole basis system means that we are going to manufacture a hole, and the limits on the hole is fixed. Upper limit, lower limit, and what with the variation in between is fixed. Upper limit, lower limit is fixed, means variation in between. They will occur on their own, but will not cross the upper limit and lower limit. So for hole basis system, the size limit on the hole are kept constant. Size limit on the hole are kept constant. Suppose we have made a hole, and these are the upper limit and this is the lower limit, and we are not going to change it. Now to obtain different types of feet, we have discussed slightly the two types of feet. One which which assembles easily due to clearance between the two assembly, and one we for the assembly of those two parts we have to apply some pressure due to interference between the two. So one is called the first one is called the clearance feet, and the second one is called the interference. We will study clearance feet and interference feet in details later on. So to obtain different types of feet like clearance feet, interference feet and transition feet, three types of feet, we will vary the dimension on the shaft. We have manufactured hole for different these same holes which will vary between two dimension, lower limit and upper limit, will be used to obtain different types of feet. Same type of hole or the hole within same prescribed upper and lower limit will be used to obtain clearance fit, will be used, may be used to obtain interference fit, or may be used to obtain transition fit. So this type is known as hole basis system. Shaft basis system means we will first manufacture the shaft, will specify the upper limit and lower limit. Now to obtain different types of feet, we will vary the limits on the hole. For shaft basis system, the limits on the shaft is fixed. We are varying the limits on the hole to obtain the fit. And for hole basis system, the limits on the hole is fixed and we are varying the limits on the shaft to obtain different types of fit. But why these two type of system is required, that is hole basis system and shaft basis system? Let's start this. So when we go on making a hole, there are some standard tools. Suppose we have a drill bit, we have a reamer, and they will be available in some standard dimensions only. So when suppose we have to manufacture, we have to make a drill of 25 mm and we have drilled and we have finished with a reamer also, and it is of 25 mm. Now shaft whose basic size is 25 mm can be turned to any diameter or in a diameter range such that for the hole which has been made with a standard tool will provide clearance fit or interference fit. So why we are not doing same with the shaft? If we are doing same with the shaft with some standard, that will be shaft basis system, but shaft basis system is rarely used because there are standard tools for hole. For shaft we can vary the dimension easily on the lathe machine or on the CNC machine or any other machine or finishing process. We can do that, non-conventional machining or any other thing we can do that. So hole basis system is preferred over shaft basis system because of the standardization available for the hole, and shaft dimension can be easily varied on the machines or machine tools. Generally for hole basis system, basic hole is used, and for shaft basis system, basic shaft is used. I am telling this generally, not necessarily that theoretically it's not necessary that for hole basis system basic hole be used, but generally and practically for hole basis system basic hole is used, means capital H fundamental deviation hole is used, and for shaft basis system basic shaft is used, that is fundamental deviation a small h shaft is used. So now we'll slightly move to clearance and interference fit. What is the meaning of clearance and interference fit? Clearance fit, let's understand like this. Clearance fit means when we are going to manufacture any product, they are manufactured in lot, means a lot of products are manufactured on the same machine under the same process parameter. Suppose that we are going to machine this pen, a stylus pen, and if it is to be machined on some CNC machine, the outer periphery are there to be machined, the single item will not be manufactured. Single item will not be machined. One will be machined, then 2, 3, 4, 5, like thousands of such pens will be machined. Suppose that 10 such pens are machined. Now 10 such pens are machined, and suppose that there is a cap to this pen also. Cap to this pen also. So all these 10 and the cap should be tight on this pen. So it should interfere with this pen. So a heat will be, first we are coming to interference feet, So a heat will be interference feet if we select any cap, that is the hole, and if select any shaft, that is the pen. Any hole, any shaft, any pair you बनाए, or when we assemble it, there should always be interference. When this will happen? This will happen if the hole, which is the cap which is being inserted in this pen, if the hole diameter, the largest hole diameter is also a smaller than the smallest shaft diameter. Largest hole diameter is also a smaller, largest hole is a smaller than the smallest shaft. If largest is a smaller, then all other shaft will be a smaller than the smallest shaft. That means if largest hole is a smaller, all other hole will be a smaller than the shaft, than the smallest shaft also. And then interference will occur, and this type of heat will be known as interference heat. For clearance, suppose another cap we are manufacturing, and that cap should always provide some gap between the cap and the pen. So the smallest cap should be greater in diameter than the largest shaft. If it is so, then the larger cap will be greater in diameter than the largest shaft, and it will also be greater in diameter than the smaller shaft. So if the smallest cap or a smallest hole is larger than the largest shaft, then always a clearance heat will be generated. Means we are taking a hole from the hole lot, we are taking a shaft from the shaft lot, and any pair you can take, there will always be clearance. Then such type of lot combination of hole and shaft will be said to give clearance feet. So let's represent this clearance feet and interference feet on zero line. So this is clearance feet. So let this is our hole, and shaft should be, don't show zero line, we actually get confused by drawing the zero line. I am deleting this. No need to show zero line, no need to show zero line. So this is hole and this is shaft. You are seeing that this is the smallest diameter of hole and this is the largest diameter of shaft. This largest diameter is below the hole, so there will always be clearance. This is the gap. This largest diameter is less than the smallest hole. There will always be some gap. When the gap, there is gap between these two. For all other pair there will be gap or clearance, and this will be the case of the clearance feet. This gap will be the minimum, and this is known as minimum clearance. And this gap, when hole is largest and shaft is the smallest, this gap is known as maximum clearance. Now come to interference fit. Interference fit. Let this is shaft and this is hole. So a smallest shaft is greater than the largest hole. So this smallest shaft will be greater than the smallest hole also. And largest shaft itself will be larger than the smaller shaft, and therefore larger shaft will be greater than the any of the hole. And so this type of fit, when the shaft tolerance zone, this is above the hole tolerance zone, this is above it, is known as interference fit, and this is known as minimum interference. This value is known as minimum interference. Why this is minimum? Because shaft is minimum diameter, minimum amount to interfere, and hole is maximum diameter, and this is known as maximum interference because shaft is maximum and hole is minimum. So we have understood the minimum clearance, maximum clearance, minimum interference, and maximum interference. Thank you. Looking forward to see you in the next lecture.